Thanks so much for the introduction and to the organizers for giving me the chance to talk to you all about the work I and my group have been doing. We've been trying to measure the isotopic abundances of dwarf stars. Though I'm giving the talk, this is work that's the result of contributions from a lot of people whose names are written here. So just to briefly set the stage, because we know these talks are quick, in a nutshell, everyone here knows that these days, many different studies in the near infrared or in the optical regularly measure dozens of elemental abundances in different stellar spectra. It might be solar twins or even M dwarfs or metal poor stars, but they make these abundance measurements of various elements, look as easy as could be. So what our group set out to do was to see if we could extend this sort of work that's being done even a little bit further to try to measure a number of isotopic abundances in nearby dwarf stars, specifically 13 carbon and 18 oxygen. And as I'll explain, we do this using the CO isotopologues. And the reason we chose these in particular is the CO molecule absorbs very strongly. And although these two isotopes have been measured a lot in evolved stars, red giants, for example, as far as we could tell, the combination of these hasn't actually been measured before in any other dwarf stars except for the sun. If you know of other measurements that we missed, please let me know. We'd be glad to hear about those, but that's what we were able to figure out. So why might you want to do this? Just one example. Of course, galactic chemical evolution models predict specific trajectories through abundance space, whether it's isotopic abundances or any elements you care to study. This plot here on the vertical axis shows the oxygen isotopic ratio, and the x-axis is the carbon isotopic ratio. And these models predict that you might start up here at low metallicity at high isotopic ratios and evolve your way down toward where the sun is down here at the lower left, and the local ISM, even a little bit lower and a little bit lower to the left. So you could imagine that you can go out and measure local dwarf stars, especially low mass ones whose compositions haven't been changed by nucleosynthesis, and you could more or less directly test how well these GCE models are performing. So we did this using carbon monoxide. As many of you know, this is a very favorite molecule for infrared absorbers. The strongest fundamental rho vibrational band is out here at 4.5, 5 microns or so. And that's, the opacity here is about 100 times stronger for a given isotopologue than it is in the K band, where some near infrared observers are maybe more familiar with CO absorption. But for these weaker isotopologues like 13C16O, in the sun at least, this is 90 times less abundant than the most common isotopologue. And so you really need this boost in the opacity in the fundamental band in order to see these lines at all. We and some other groups have tried looking for these isotopologues in the K band at the first overtone, but the lines are really weak, and especially in later type stars, it's just really tough to see them and be confident. So I think you really have to go out to the M band, the thermal infrared, to do this. I think there's only currently 2 instruments that can even make these measurements. We used iShell and the IRTF, a very high resolution infrared spectrograph. When CRIRES Plus eventually comes back on the VLT, then I think there will be 3 instruments that can do this. But it's still very limited facilities that are able to make these measurements. Because what we need to do is make very high resolution, very high signal to noise observations of these stars. And so what you see here is a model at top, and then 2 of our observed spectra of 2 M dwarfs that are in a wide binary. At first, it just looks like lots of noise. You think maybe that's just lots of tellurics. But if you start comparing to the model, you actually see that there is some noise, but most of these features are really real. This is a resolution 70,000 spectra at 4.5 microns with signal to noise of 40 or so. And so we're easily seeing many of these lines by eye. But none of these lines that you can make out by eye are actually the isotopologue lines. To see those, we really have to resort to stacking all of the clean lines of these isotopologues. And so when we do that, say for 13CO, which is shown here, you see a really nice line profile right at 0 relative velocity, right where all of these 13CO lines ought to be. And so we clearly detect this isotopologue in these M dwarfs. And we compared these to a number of model stellar spectra using the Phoenix code made by Josh Lothringer. And if you imagined that these M dwarfs had solar-like abundance patterns, that is the carbon abundance scaled as the metallicity, for example, then you would have predicted this green absorption line, which is much deeper than what we really observe. So we already can see that these M dwarfs, their isotopic abundances don't follow strictly solar scaling. No reason they should, but they don't. So we can compare to a variety of models and see, for example, that it's about a third of what I would have called the nominal 13C abundance in this star. So not only could we do this for 13CO, we were also able, by the same line stacking approach, to see C18O as well. It's less abundant, just like it is in the sun, but again, it's not quite at the nominal solar scaled abundance. It's a little bit less than that, as shown by the data here. And we think this is the first time 18O has been seen in any M dwarfs at all. But again, if you know of other things that we missed in the literature, please do let me know. We'd be happy to hear about that. So our isotopic ratios that we measure for this M dwarf binary is strongly discrepant, actually, with these GCE models. That blue model track is shown over here on the left, and especially the 12C to 13C abundance ratio here is off by something like a factor of 2 or 3 from what is predicted by some of these models. So that's
2 minutes.
Thank you. That's a little interesting and tough to explain. In our paper, you can sort of make an ad hoc model that enriches this material with some supernova ejecta that gets you to the right abundance patterns. That's a little unsatisfying. And so what we're working on now is expanding our sample to see if this binary is an outlier or if this represents general trends. So we're expanding our sample a little bit. We're looking at these same isotopologues in some solar twins, for example. So here's the 13CO equivalent width versus age of some solar twins. Maybe there's a trend emerging. This is only 7 stars, including the sun. So it's still preliminary work. If we stack all of these, we actually see C18O as well, but it's really faint in these hotter stars. So we're working on interpreting that as well. My student David Correa is working on that here. So in summary, we think these are the first multi-isotopic measurements of dwarf stars outside of the sun using the CO fundamental band and the M band. These definitely don't match the predictions of GCE models. We're working on expanding the sample. I think these could be a powerful tool to test galactic chemical evolution and also compare for planet hosting stars, compare stellar abundances to the planetary abundances. So that's it, and happy to take questions. Thank you.
Thank you very much. Very interesting work. So there is a question by Roy van Boykel. Is the stack of 13CO lines an actual stack or a cross correlation with the 13CO model spectrum, analogous to what is done by Snellen and many other scenes?
Sure. Thanks, Roy. Hope you're keeping well out there. It was just a straightforward line stack of the lines. I think in velocity space. It wasn't a cross correlation. We thought about that, but there are just so many other extraneous lines in the M band. Yeah, something worth exploring, but it wasn't a correlation, just a stack.
Okay, time for another question from Tomek Kamiski. Are the abundances derived from comparison to full model atmospheres or separate molecular fits? Are corrections for optical depths included?
I'm sorry, I missed part of the question. Something about the stellar modeling?
I read it again. Are the abundances derived from comparison to full model atmospheres or separate molecular fits?
Right. Right. So the abundances are derived from the model Phoenix spectra that Josh Lothringer was running. So this is full spectral synthesis. It's not curve of growth or equivalent width. So a full-on spectral stellar atmosphere model and model spectrum.
Okay, and the second question was, a correction for optical depth included? Okay.
I'm not sure exactly what you mean by that, but feel free to send me an email and I'd be happy to talk more.